Good morning, good afternoon, and good evening. Welcome to part 2 of the Web 7.0 DIDComm Agent Architecture Reference Model presentation. This is based on the white paper of the same name, and part 2 is going to cover the second half of that white paper. My name is Michael Herman. I'm a self-sovereign blockchain architect, developer, and futurist. And I live on a cattle ranch in southern Alberta. And you might wonder what cattle ranches have to do with digital identity, but there's actually a fairly rich collection of attributes and connections and relationships that can be found on any farm. When I'm working as a self-sovereign blockchain architect, I sit here in my picture window in my little farmhouse, and this is the view that I have. Before we get into the meat of the things, I just want to highlight this concept of first principles thinking. I am by my nature a first principles thinker, and you're going to see some artifacts of that in this talk. A first principles thinker always deconstructs complicated problems into their most basic core elements, and then will reassemble them or synthesize them from the ground up. So artifacts of that you're going to see are some new concepts, some new terminology being introduced into the DIDComm community. You're going to see some clarifications and sometimes some repurposing of some terms. And I just want you to make you aware of that up front and some of the reason for that. Just a little bit more about my background. I guess I've been building, message-based, message passing, decentralized applications for a gazillion years, starting back in 1986. This is the world's simplest Windows application that shipped with Microsoft Windows SDK 1.0. It's showing the message loop that's receiving event messages from the Windows operating system environment, translating those and dispatching those, and they get dispatched to that function at the bottom, main WinProc, and it could be a command to repaint the screen, or it could be a command from the menu bar. Dozens and dozens of events within the Windows system, and even today, what's referred to as the Win32 programming model is still available in Windows. And I was an original Windows developer back in '86. Going through these a little more quickly, I've built a lot of architecture reference models. Part of my training is I have a Bachelor of Mathematics in Computer Science, a Master's of Mathematics in Computer Science. I'm an enterprise architect by professional training as well. I often use a graphical language called Archimate, which you see here. I use this in a fairly large article on GitHub to describe the Alice buys a car scenario for Hyperledger. In the 2000-2001 timeframe, a fellow named Ray Ozzie founded a company called Groove Networks. That's a decentralized platform, decentralized group collaboration platform, to which partners could develop custom tools that would plug into these decentralized workspaces, these decentralized group collaboration workspaces. I bring this up because it's been around for about 20 years. And a lot of what we're seeing with DIDComm is not brand new. There is a white paper called The Design of Graphics Processors, which coins the term the technology wheel of reincarnation. And to some extent, what we see with DIDComm and what I'm calling Web 7.0, the DIDComm Agent Architecture Reference Model was already available as a commercial product back in that 2001 timeframe. I'll talk a little bit more about Groove. It's been very influential in what you see here in the DIDComm-ARM. This is a reference model for the sovereign glossary. All the terminology that's used in the sovereign governance documents. This is the Hyperledger Indy and Hyperledger Aries architecture reference model. These are all interactive tools. There's an interactive explorer for walking through the models and different views of these models. This is depicting the DIDLang language for working with DID methods, DID identifiers, DID documents, DID agents, DID objects. It's a full CRUD, create, replace, update, and delete language, much like SQL Server. Think of it as SQL Server for the decentralized world. Daniel Hardman and I had collaborated on a architecture reference model for Aries agents, and that's what you see here. This is part of the Aries RFC 004. I have a lot of background on the Microsoft platform, on the Microsoft stack. So this is Microsoft Azure Stack, which is a version of Azure, their cloud platform that can run on-premise. Some stuff I did for the Enterprise Data Vault efforts within DIF. More related to that. This is the Universal DID server for the Trusted Digital Web. I'll talk a little bit about this. This is a way of using the extendable, customizable architecture of DNS to support all the elements of a DID document and enable the storing of DID documents in a DNS server. There's a web page that was actually served up. If you look closely at the address bar, it was actually a DID that was used to index or reference this web page. I've worked on DIDComm protocols. This is the verifiable capability transaction protocol. I forget exactly what it was, but back and forth confirmation of a verifiable capability authorization before you actually receive a copy of a VC. The Trusted Digital Web is kind of this overarching project that's been guiding me for over 5 years, architectural model for that. This is the last one of these slides, and really kind of characterizes how my thinking started here about, first of all, making sure business documents, purchase orders, invoices, waybills, delivery confirmations are first-class citizens in the DID core. You'll find me named as a named contributor to DID core, and my main claim to fame is making things first-class entities. Also, that extended into the work with Drummond in the sovereign glossary. But specifically here, I had this idea that if you think of an ERC20 token on Ethereum, it really just has a single method for transfer, for the transfer of value from one address to another address to another address, which to me has negligible business value. But what if, instead of just value tokens, you had the ability to submit an expense report or a timesheet or a contribution report, any sort of requisition into that smart contract, so that the smart contract could then arbitrate that contract either by applying business rules that says if it's below $100, we're just going to automatically approve it and we're going to pay you with Ethereum. Or if it's between $100 and $500, we're going to route it to an accounts payable clerk, and they're going to have an app that is going to look at the smart contract and look for expense reports that are waiting for their adjudication. Or if it's over $500, maybe it has to go to your manager for approval and subsequent payment. So the idea of taking this idea of transferring tokens, but having that initial token be an actual business document. And it's from there I made sure the business documents were first-class citizens in DIDComm, that verifiable credentials are good containers, great containers for representing business documents, and so on. Okay, this is the title page for the white paper. The DIDComm Agent Architecture Reference Model, DIDComm-ARM. And it's really intended to be, originally intended to be a design guide for software architects and developers building decentralized agent, DIDComm Agent-based software systems. And this presentation and the previous part 1 presentation go through that white paper literally page by page, and enable me to provide a little more color, a little more annotation on top of the text that you'll find in that white paper. So the purpose and intended audience of the white paper, and hence this presentation, is to introduce and describe the DIDComm Agent Architecture Reference Model and the DIDComm Notation. The DIDComm Notation is a graphical modeling language used to design and model DIDComm agent-based software systems. So, harkening back to my experience as an enterprise architect and using the Archimate enterprise architecture modeling language, I knew I was going to have a lot of diagrams. There's some 50 or 60, 70 figures in this white paper. And I needed to have a consistent modeling language for representing all the different concepts. So I said, well, let's formalize it. Let's call it DIDComm Notation. And so the first part of this talk, the first part of yesterday's talk, the part 1 was to describe the DIDComm Notation. I actually will not spend very much time on DIDComm Notation specifically in this talk. The DIDComm-ARM is a layered architectural model designed to help guide software architects and developers in the design and creation of the broadest range possible of DIDComm agent-based software systems. And the intended audience is, again, primarily people involved with software architects, developers, user experience specialists who are creating DIDComm-based software systems. It will also be of interest to those that are involved with the range of standards efforts related to decentralized identity, verifiable credentials, secure storage, the DIDComm protocol, etc. So at the beginning of the white paper, I set out 3 specific goals. To better understand the active components of DIDComm agent-based software systems and how they rely on each other and how they interact with each other. Introduce a new graphical modeling language, the DIDComm Notation I spoke to earlier, to help visualize these new architectures and designs. And finally, to describe that layered architecture model. There's 7 layers in the DIDComm architecture reference model. And it is to help guide and design, the creation of the broadest range of software systems possible. But it was also designed to be teachable, to make DIDComm and DIDComm agents very easy to understand. Just a little intellectual property rights statement. So this white paper is licensed under the Creative Commons Attribution Share Alike International Public License. The important part here is that it's a Creative Commons license, which means the content can be used broadly. The more important part is the attribution share alike formal clauses that are part of that version of the Creative Commons license. That requires attribution to be carried forward, the copyright statement to be carried forward in any derivative works and in any derivative of the derivative works, adaptations, etc., on and on. That just happens to be something that's important to me. Regarding trademarks, well, there's been a recent kerfuffle where the Web 5 people were thinking of trademarking Web 5. I'm not doing that. There's a specific phrase there in that bottom paragraph that says the phrase Web 7.0 is not trademarked. It's not protected anyway, but there are some graphical logos that I have trademarked, and you see some examples of them here. And that's really just to identify more formal publications of content related to Web 7.0. Just another caveat, this white paper is neither a W3C, DIF, Sovereign Foundation, or TOIP publication, unofficial, official, or otherwise. It's an independent production produced by the author being. Okay, so this is actually the layer 6 model, the actual Web 7.0 architecture model. And I just put this up here right at the beginning so you get a sense of where we're headed. So it's a very comprehensive model. There, below the red line, there's the DIDComm network. That's a global message passing and delivery network for DIDComm messages. It relies on the DIDComm mediator / relay agent concepts, the forward DIDComm protocol. I focus almost exclusively on DIDComm running over HTTP, but on the left-hand side, left bottom corner there, all the principles that I refer to here could also apply, to DIDComm over Bluetooth, DIDComm over libp2p, DIDComm over WebSockets, DIDComm over gRPC. To some extent, some of those have to be proven out, but the intent is for this to be an architecture reference model, so for it to work anywhere. Above the red line, we call that the Web 7.0 network, and that's where all the agents live. DIDComm clients, DIDComm agents, and what we call DIDComm user agents. And so we're going to start with layer 0, which is just 2 REST over HTTP agents talking to each other, or from a client to the agent. We're just going to go in the one direction. There's no DIDComm anything involved in layer 0, and then from there we're just going to layer things on very gradually, very incrementally, until we get to this layer 6, Web 7.1. To put a little bit more context about what Web 7.0 is, the left 2 diagrams here are from the Computer History Museum. And they're used to characterize or differentiate, the internet from the web. A lot of people use those words interchangeably. They're quite different. The internet came first, and it's this global communications network for connecting devices. So it's the baseline raw packets that are being sent, over your Wi-Fi connections and over all the different routers and backbones and stuff that make up the internet. The Web 2.0, 3.0 is about connecting people to centralized websites and services. That maybe wasn't the original intent, but that's certainly the way that it is today. Connecting people to centralized websites and services, and email being one of the most prolific or most common service there. And so you can think of, if you put your left hand on top of your right hand, your left hand on top of your right hand, the left hand is like the web, and it's running on top of the internet, which is your right hand. And then we get to the right side of this slide, Web 7.0. It's about connecting individuals to each other. Individuals to each other via their trusted personal agents. And when I say individuals, I'm talking about individual people, but also individual organizations and companies, farms, grocery stores, connecting them directly to each other via their trusted personal agents. So if we use that analogy of putting your left hand on top of your right hand again, the right hand on the bottom is still the internet. That second left hand that you put on top now, that's Web 7.0. So looking at this kind of block diagram, you see that Web 7.0 and Web 2.0, 3.0 are different and separate. And they run on devices that are connected to this global communications network at the bottom. So Web 2/3.0 has web browsers, web servers, HTTP protocols, web pages, web data, all the things you've come to know and love about the web, the World Wide Web. Web 7.0 is about DIDComm protocols, DIDComm agents, DIDComm messaging with attachments, of which I feature VCs, but it could be almost anything. The DID registry for resolving DIDs to service endpoints, and then the decentralized identifiers themselves. Just to be clear, there are no websites in Web 7.0. It is all about trusted personal agents talking to trusted personal agents. They do coexist on the same internet network so that they can interoperate. But just to be clear, Web 0.0 does not have websites. It's entirely based on DIDComm Agent. Okay, so with that as an introduction, this is the sort of the high level, I sometimes call it the feature matrix, which represents or visually depicts the 7 layers of the DIDComm agent architecture reference model. So we start in the bottom left corner where it says layer 0. In the layer 0 model, we're going to show just plain old HTTP, a client talking to an HTTP agent and sending a plain text message. Again, if you remember, the overarching goal is this is to be a guide for software architects and developers building software systems. And so we want to start with a common denominator. We want to get everybody on the same bus, same tour bus here. And so we're going to start with REST over HTTP, or REST over HTTP scenario. And then we're going to move up to layer 1, right above it. So what's the difference? What's that vertical axis, DID addressable agents? Well, DID addressable agents in layer 0, we're just using plain old domain names or IP addresses and ports to address or name or reference those agents. In layer 1, we're actually using DIDs to name those agents. And so that requires us to do DID resolution. We need to be able to take that DID, resolve it to a service endpoint, extract the URL, and then we effectively have a layer 0 type of scenario. But that's an example of just the baby steps we're trying to take. We're still doing REST over HTTP. We're still in layer 1. We're still communicating or transmitting simple text messages, plain text messages. But we've introduced the concept of DID addressability. So once we're in layer 1, then we move from left to right and along the message passing protocol axis. And if you look at the bottom of the diagram there, it says REST over HTTP where we started. Then we go to DIDComm messaging, just basic DIDComm messaging with attachments, and then DIDComm agent mesh networks. So those are layers 1, layers 2, layer 3, and layer 4. Once we get into layer 1, 2, 3, 4, we're also in the world of DIDComm. So all of those scenarios are DID addressable, use DID addressable agents. So if in layer 1 we understand DID addressability, we've introduced the concept of a DID registry, we've introduced the concept of mapping a DID to a service endpoint and extracting its URL. We use that exact same concept in layer 2. The only thing we add here is instead of transmitting a plain text message from the client to the agent, in layer 2, we introduced the concept of DIDComm messages, which are authenticated encrypted messages, and that can only be decrypted by the receiver, and in turn can be authenticated by the receiver to assure the receiver that it was only a particular sender that sent them that message. So layer 1 to layer 2 is just about what we call inbound and outbound processing. In the outbound processing, we do authenticated encryption. On the inbound processing, when we receive one of these DIDComm messages, we do decryption and authentication. To go from layer 2 to layer 3, we take those same DIDComm messages that we learned how to create in layer 2, And we add the ability to attach more structured data, if you will, to your DIDComm message. So a verifiable credential is a classic example, an MDL driver's license, an X509 certificate, a PK zip file, a Word document, an Excel spreadsheet are all examples of attachments that can be added to a DIDComm message. So again, just an incremental baby step moving from layer 2 to layer 3. It's just about adding attachments. In layer 1, layer 2, and layer 3 so far, we've just talked about point-to-point communication, direct communication between a client and an agent or between two agents. Layer 4 takes us quite a significant step up in that it defines that area below the red line, a DIDComm network, a routable global delivery network for DIDComm messages. And so we refer to that as the DIDComm Agent Mesh Network model, and that's layer 4. Layer 5 can build on top of layer 2, layer 3, or layer 4, typically layer 4. And we call that layer the DIDComm user agent model. The idea that we're going to create a specialized DIDComm agent called a user agent, and a user agent is different from an ordinary DIDComm agent in that the user agent has a user interface. It has a UX. It's an agent that interacts with people. It's an agent that's on the edge of the network that can interact with humans. Layer 6 takes layer 5 and kind of adds the fit and finish. We talk about things like virtual web drives, which can be instantiated as decentralized web nodes, solid pods, Trinity graphs, etc. And it's actually, you know, the Web 7.0 model that we're truly trying to realize to the point where at the very end I'll talk about it maybe maturing into an actual DIDComm-based, you know, network operating system, spanning the globe, providing those, connecting individuals with trusted digital agents. Okay, so let's take that last picture and just pull it apart, just to make it a little bit easier to chunk it and make it a little bit easier to understand. Move that over to the right-hand side, and we add these two blocks, rectangles on the left. This is what the white paper looks like. It starts with the DIDComm Notation section. It does an overview of the first 5 layers. And then it does a drill down on the on those first 4 layers, and then it does a drill down on layers 4, 5, and 6. And part of the reason why these blue rectangles are separated like that is layer 5 and layer 6 came into the picture late. And I'll talk a little about that a little bit later. So they're actually described in appendices of the white paper. Yesterday, I recorded part 1, which covers the DIDComm notation and does an overview. You should probably watch that first if you haven't watched it already. In this talk, part 2, we're going to do a drill down on the core layers and then the Web 7.0 layers. So let's start in on those core layers and do a drill down. So this will, to some extent, have a little bit of a repeat of the last half of yesterday's talk. Okay, so the layered model drill down. So the DIDComm-ARM is a layered architecture reference model designed to help guide software architects and developers in the design and creation of the broadest range of DIDComm agent-based software systems. So layer 0, what's the purpose of layer 0? So this is to provide the common technical foundation that a vast majority of software architects and developers around the world will be familiar with, regardless of their preferred technology stack. Each subsequent layer then builds off this common technical foundation and also the other preceding layers in the DIDComm-ARM technology stack. So here we see the DIDComm notation representations for an agent on the left and a client on the right. The agent on the left has two interfaces. The client only has one. The client, that arrow on the client, the arrow interface, if you will, on the client, that's called the origin in DIDComm notation. We actually pull out the concept of the origin as the place to which messages are sent out of the agent, and you can see that messages come out of the client on that arrow interface, and they're received by the agent on the left with that interface that has the round circle. The round circle interface is the typical traditional service endpoint that you know and love. And we can see that there's a plain text message, a timestamp that we're trying to send from the agent, aka client on the right, to the agent on the left. Now, in the REST model, we don't have DIDs, we don't have DIDComm. That stuff's to come in the subsequent layers. All we have here, all the client on the right has, is hopefully knowledge of the service endpoint address and port for the agent that's to be the receiver of this message. So we can see underneath where it says REST over HTTP agent, that service endpoint has a URL of example.com:8080, and if you do a NS lookup on example.com, that's the real IP address. So ultimately, all communications on the internet has to come down to a numerical IP address and port. And so how does this client know what that numerical address and port is? Well, we don't have too many options actually in this particular model. We could either hard code that IP address, port, and path in our application, or we could hard code the internet domain name, port, and path, or we could use a local host file to look up that domain name and get an IP address, or we might have a DNS server available to us, or the domain name might already be registered in a global domain server, DNS server. But ultimately, we have to reduce things to a numerical IP address, port, and path, and of course protocol. This is true not only for layer 0, but it's true for all the layers. I'm only doing this for layer 0, but this is what the documentation in the white paper looks like for layer 0. Now this is only 2 pages. Typically there's the same diagrams we see in the presentation, plus a narrative that describes it. And then if you see on the right-hand page, it says layer 0 REST over HTTP agent model workflow. So there is a step-by-step workflow about how a message is transmitted. And so as we get into the more elaborate scenarios, for example, DIDComm messaging or DIDComm messaging with verifiable credential attachments, the steps get significantly longer. But I'm just showing you that as an example and in motivation to go look at the white paper. So we're not doing question 2, but let's look. We've gone from layer 0. Let's go to layer 1, and we're just taking what we saw, and we have now people, Bob and Alice, and Alice wants to send a message to Bob. So at a conceptual level, that's what we're doing, but we know that we can't actually send messages between 2 personas, between 2 subjects. What we really need to do is send a message from Alice's client or Alice's agent over to Bob's agent. And that's what we see depicted here. So the outside characters that represent the person, we call those personifications. That's a new term that was introduced in part 1 of the yesterday's talk. Personifications. And it's personifications that are named by their DID. So Alice's personification is did person 1 2 3 4, and Bob's personification is did person 5 6 7 8. The software agents are not identified by DIDs. There's a popular misconception about that and confusing terminology. Software agents are named or identified or addressed by their service endpoints. They might have more than one service endpoint, but they are addressed by their service endpoints. So we have this conundrum. Alice, who's known as did person 1 2 3 4, and Bob, who's known as did person 5 6 7 8, are trying to exchange a message. They're trying to communicate with each other. How do they do it if their agents are using a scheme that's different? The way you do that is through DID resolution. We need to start with the DID of the receiver, in this case Bob's DID, and we use something called a DID registry to resolve that DID to its associated DID document. We're going to see examples of that. From the DID document, we'll extract the service endpoint URL, the protocol, the address, the port, the path. And if some of those aren't there, there's defaults that will be assumed. And then we need to take that service endpoint URL and resolve it to an IP address, just like layer 0. So really what's layer 1 is doing is just adding those first 3 steps, resolving or translating or looking up that DID, that decentralized identifier, and mapping it to a service endpoint of the agent. So at this point, we're getting pretty close to being able to enabling Alice's client to talk to Bob's agent. So we do that by introducing the DID registry. DID registry stores DID documents. And so here we can see that Alice's client has taken Bob's DID, the did person 5 6 7 8, queried the DID registry, received a DID document there, the green line. And from that DID document for did person 5 6 7 8, Alice's client, Alice's REST client, because we're still not in the world of DIDComm yet, Alice's REST client is going to take that DID document, find the service endpoint elements, extract the URL for the service endpoint element. It's going to be, example.com:8080, like we see on the left-hand side. And then Alice's agent can use that URL, resolve it to an IP address, 93.184.216.34:8080, and send that message over to the service endpoint of Bob's agent. So Alice does that on, again, what we call her origin interface. That's the interface that has the arrow. And when we talk about service endpoint addresses, it's about the the interface that has the circle or the ball on it. This is what a simple DID document might look like. At the bottom half, you can see a service endpoint of type REST agent is defined, and it has an ID of REST agent 1, and we can see that the service endpoint is example.com:8085. So in the previous scenarios, we talked about Alice's client talking to Bob's agent. Well, we could have Alice talking to a bank. We could have Alice talking to a farm business, David's Cabbages. We can see that Alice still has did person 1 2 3 4. She may have multiple decentralized identifiers associated with her. Over on the left, we see David's Cabbages. It's got a DID of DID::org: 001 002 003. We could have two companies talking to each other. ABC Groceries talking to David's Cabbages. Maybe they want to order some. So we've just finished talking about layer 1. All we've done in going from layer 0, which is plain old REST over HTTP, to layer 1 is we're still not using DIDComm messaging. We're using plain text messaging, but we're using the DID registry to look up, resolve, map a decentralized identifier, the DID::org: 001 002 003, to a service endpoint URL. So we can in turn get the numerical IP address and port and send the message across. So let's take that layer now and move to the right and layer 2. So layer 2 builds on layer 1, and the idea here is just to introduce a single concept called DIDComm Messaging and DIDComm Messages. And the only thing that differs between the two is that DIDComm Messaging, these authenticated encrypted messages now are going to replace the plain old messages. So how do we do that? We represent that in DIDComm notation. So this looks like the diagrams we just saw, Alice and Bob. But in this case, you'll notice the purple artifacts. There's the line from the client origin interface, from the client arrow, over to the DIDComm agent service endpoint on the left. And you notice that it's kind of a triple line. It's kind of got a shield or a sheath on it. And so that is what we use to represent the transmission of that authenticated encrypted message. The other thing is on those interfaces now we have little purple boxes. So if we start on the right, the DIDComm client, and we can see the purple box on that arrow, that's called outbound processing. That is the extra step that DIDComm agents and DIDComm messaging adds. Outbound processing is the step that uses the public-private key pair for the client and the public-private key pair for the agent to do this authenticated encryption. And we call that outbound processing, and that's what the rightmost blue box is. It's outbound processing, authenticated encryption, using the relative key pairs of the sender and the receiver, so that when it's received on the agent side on the left, that purple box is called inbound processing. It's the step that knows how to do the decryption and authentication of the message that's coming in. And otherwise, this is exactly the same as the REST over HTTP model. So very simple addition, very simple change. I'll mention at this point too that there are code samples being prepared, operational code samples for all the DIDComm agents and DIDComm clients, the DID registry, the DID relay server, that will become available as part of this package. Okay, so here's the big picture again. We've added the personifications, if you will. So ABC Groceries personification is an organization, and it's using a graphical element, a DIDComm notation element representing a grocery store. And it has a DID called DID::org: 444:555 or -555-666. If we look on the left-hand side, we have David's Cabbages, and it's got a DIDComm agent, and it's running on port 8090, And it's got a personification, which is a farm business. That's the subject or the persona that's associated with that DIDComm agent. And it has a decentralized identifier of DID:org, :111-222-333. And the way that we communicate between these is the same as in layer 1. We need to resolve that DID:org, :111-222-333 for David Cavage's persona, and get the DID document, get the service endpoint, and then get the URL out of that service endpoint. That's what we see here. So ABC Grocery is trying to send a purchase order for 10 cabbages over to David's Cabbages. So its first step is to do an inquiry or a query or a read against the DID registry, passing in 111-222-333 to get David's Cabbages DID document. We'll get the service endpoint and the URL from that DID document, and we'll do the outbound processing of that message, and then we will send it across. That authenticated encrypted message, we'll send that across to David Cavage's agent, where the little blue purple box there will do the inbound processing to do the decryption and authentication. Next to the hats on the agent and the client, we see smaller versions of the personification graphical elements or icons, and that's just to remind us that sometimes we start talking about the agents as if they have DIDs and things become complicated. I'm going to use a more robust example in a minute, but that's just a shorthand, so you don't have as many large DIDComm notation elements in your diagrams. Because we're talking about DIDComm agents, we just introduced DIDComm agents. I'll mention here that we can also, on top of that core protocol for sending a message from one agent to another, you can build custom protocols. And Daniel Hartman, has suggested, this is a potential list or hypothetical list of what custom DIDComm protocols might look like. And you can look at those afterwards or pause the video. Okay, so we finished layer 2. Layer 2 is different from layer 1 in that we replaced the transmission of a plain old text message with outbound processing, which created an authenticated encrypted message. We sent that across, and we received that and put it through inbound processing, which did the decryption and authentication. Let's again take another step here with layer 3, where we use that same messaging paradigm, the same mechanics we've just described, that we've been building up to, and we're going to add the idea of DIDComm message attachments. And here we're going to kind of lean in on verifiable credentials, because verifiable credentials are good for representing business documents, my favorite topic: purchase orders, invoices, way bills, delivery confirmations. And so that's the purpose of layer 3, is to add. So as just a reminder, this is where we left off in layer 2, just a slide or two ago. And the only thing we're really trying to do now is in outbound processing, or before we do the outbound processing, we want to be able to attach some sort of structured data. It doesn't have to be a verifiable credentials. It's just a good example. And verifiable credentials are very decentralized-ish way to do things. We're going to look at a bunch of other kinds of attachments here in a moment. So things really haven't changed too much. We're just making the payload that we submit to outbound processing a little more structured, a little more complicated. It gets transmitted exactly the same from ABC Grocery over to David's Cabbage's agent. Inbound processing is going to just decrypt it and authenticate it the way that it normally would, but the structure that comes out of inbound processing will be a DIDComm message with an attachment this time. We'll have to do the DID registry lookup exactly the same. It's actually not it's not changed. It's not affected by this scenario. So that's what was introduced in the layer 1 model. It doesn't change in layer 2. And we're just highlighting the verifiable credential attachment here. It does beg the question, what would you put in the verifiable credential versus what would you put in the DIDComm message? A DIDComm message can have some structure to it. And the thing to remember is, a couple things to remember. I should have a slide on this. Verifiable credentials are plain text. They're transmitted and received once they come out of inbound processing. All the contents of the verifiable credential are plain text. Anybody in possession of a verifiable credential has the ability to read it and inspect it. So there's no privacy or encryption or anything available with verifiable credentials. So that's one thing about verifiable credentials. With DIDComm messages, they are authenticated encryption. So that means that only the receiver can decrypt it. And the receiver, after it's decrypted, is able to determine who, in an authenticated way, secure authenticated way, who the sender was. So in some respects, messages, with or without attachments, are sort of more private, more secure, than verifiable credentials. But verifiable credentials, we're able to detect whether data has been tampered with much more easily. So with that as an introduction, I introduced the concept of the authenticated conversation spectrum. And this is my contention, that verifiable credentials should only be used for normative statements, things that are facts and truths. Anything that is more non-normative, opinions, folklore, speculations, I've got a taxonomy we're going to look at in a minute. That should just be encoded as a DIDComm message. And maybe because they are opinions or folklore or speculations, they might be better served by the DIDComm message capabilities of being, supporting authenticated encryption. Maybe you don't want those floating around in plain sight. In the middle is DIDComm messages with verifiable credentials attachments. So if you need both worlds, you want the structure for factual, truthful things, let's say like a business document. But you want to have the security and privacy of the authenticated encryption. You can take that verifiable credential, attach it to the message, and do the authenticated encryption on that message with attachments. You can even store those encrypted, authenticated encryption messages with attachments in your database or in your virtual web store. And so that's just a little bit of a guidance there. To help more, I have a blog article called Facts, Opinions, and Folklore, a Preliminary Taxonomy, the page here that's on the left, and it talks about things that are the different kinds of facts. There's true facts or hard facts, things that are 100% true. There's false beliefs, things that are believed they're true but are in fact false. And then there's fake facts, and they're knowingly or purposely, 0% true or 100% false. You can have perturbations of facts, facts that are misunderstood, misconceived, misstated, or miscommunicated. Opinions, they're vague, poorly reflected recollected, subjective. They might be humorous or satirical. And at the bottom is folklore, feedback originating from a third party or a fourth party, and passed along. There's a companion blog post called Truth and Marketplace of Ideas, and it actually suggests some interesting ways of supporting truthful assertion of different kinds of opinions and facts. It's actually quite interesting, the different venues that are. So let's go into layer 4. Layer 4 is a little bit different from the rest. So far what we've done is we've looked at the the principal technologies. We've looked at DID addressability, we've looked at DIDComm messages, we've looked at DIDComm messages with attachments. Now in layer 4 we're adding the concept of DIDComm message routing, and here we see an example of that. So instead of doing just point-to-point messaging between the client and the agent, what we're doing is we're sending those authenticated encrypted messages into a mesh, into a message delivery relay and delivery network. And the purpose of this is to make the delivery more robust and more efficient. If you're delivering a message around the world, there's latency issues, so you may want to have a store and forward type of solution that's represented by a DIDComm network. The blue dots are the DIDComm network router nodes. They're actually a specialization of DIDComm agent. And the DIDComm network router nodes, or the DIDComm network router agents, they know, they have routing tables. They know about the topography of the graph. And they're able to find the most efficient, least cost way of routing a particular DIDComm, forwarding, I guess is the proper word, a DIDComm message, through that network. The other thing that the DIDComm network provides over and above this routing capability is the ability to support disconnected clients, disconnected agents. So the way that works is if an agent is not running, or the computer that it's on has been turned off, and somebody is trying to send you a DIDComm message, what happens to that message? Well, in the point-to-point scenario, that attempted transfer is just going to fail. In the layer 4 DIDComm agent mesh network model, you can send that into the DIDComm network, and those DIDComm network router nodes will cache and store those authenticated encrypted DIDComm messages. And when that DIDComm agent comes back online, somebody turns the computer on, starts the agent up. When that agent comes back online, it can query its nearest node in the network and say, hey, I'm here. Is anything queued for me? Is there anything waiting for me in the networks? Was anything sent to me while I was offline? And there's two categories of disconnected agents. There's the case where an agent is not running, or the computer it's on is not running. And then the second category is where an agent is behind a firewall. And so you can't call in to an agent that's on the inside of a firewall. So it's going to appear to be disconnected. Those messages are going to be queued in the network. And then it's up to that agent on the inside of the network then to to call out across the firewall into the network to see if there's any messages waiting for them. So in effect, it's kind of a polling strategy that needs to be utilized when, for example, there's a firewall in place. So how does, let's say, node 2 here know that it's connected to node 1, 8, and 3? Well, we're going to leverage the ability of the DID document. So normally you have a service endpoint, which would be the active endpoint of of the DIDComm agent, of the DIDComm router node. But we can also use the service endpoint concept to say, here's the service endpoints of my nearest neighbors. So in this diagram for the DIDComm agent node 1, its nearest neighbors are node 3, node 5, and node 9, highlighted in the green box. I would probably change up this diagram a little bit. Instead of using URLs in there, I would use DIDs to say that DID : message : node 1, its nearest neighbor is DID : mesh : node 3, DID : mesh : node 5, and DID : mesh : node 9. And then anybody that needs to resolve those further then can do a query at the DID documents for those respective ones. There is a concept of a minimum viable DIDComm network, and you can think of that as a single node. So let's say you just need the capability to support disconnected clients. You just need one node to do that. And so that's what we see symbolized here. ABC Grocery sends its messages to that single relay. If David Cabbages is running or has a disconnected agent at that particular time, they'll just be cached there in that node called M. This would be a simple example for just running on your desktop or for development purposes. The other thing you want to do is, for high availability, have multiple M's, if you will, and you're actually then talking about a full-on DIDComm network like we saw in the previous diagram. But this would work for testing. And as I've already highlighted, this is the same diagram that you'd use for the disconnected agent. Okay, so here we are back to the white paper outline. What we have left to talk about is what I call the Web 7.0 layers. So we need to talk about the DIDComm user agent model and the Web 7.0 model. So layer 5, the user agent model, the purpose of layer 5 is to introduce the concept of a user agent to the DIDComm notation and the DIDComm-ARM. The layer 5 user model adds the ability to incorporate specialized DIDComm agents designed to interact with human actors. So they're DIDComm agents that have a UX or a user interface associated with them. Yesterday, or in part 1, we introduced this scenario. It was actually a DIDComm agent gateway scenario where Dr. Carroll Cardiologist Clinic on the right-hand side here, they've got a line of business application for medical records. And the idea here is that they're using the file print capability and a custom device driver, printer device driver, to be able to take doctor's notes, cause them to be the print stream for that doctor's notes to be captured as a verifiable credential in the DIDFax Windows printer driver, which in effect is a DIDComm client. It's going to encapsulate that print stream in a verifiable credential. It's going to attach it to a DIDComm message. and send it to Carol Cardiologist's DIDComm agent. So that's everything that's happening in the green box. Carol Cardiologist's agent then needs to route that print stream, that DIDComm message, over to my general physician's agent over here in the blue box. And we see that in the bottom left-hand corner, the routing of the DIDComm message with the print stream attachment from Carol Cardiologist over to my general physician. And once my general physician's DIDComm agent receives that, I want to be able to view that, or my general physician wants to periodically go to her computer and look on a screen, look on through a user interface to see to read those doctor's notes. So at the top of the blue box, the DIDComm user agent represents a DIDComm agent, a specialized DIDComm agent that has a user interface, and it just calls down into the DIDComm agent it is paired with. Paired is a magic DIDComm-ARM term. So agents can be paired, and here we see the user agent, DIDComm user agent being paired with the general physician's DIDComm agent to provide that interactive experience. An example of what a DIDComm user agent might look like is this example here. This is a group collaboration / chat application. It's called Mesh, and it's available on GitHub. It has the ability to send text messages and the ability to send files. And the default version on GitHub actually uses the Tor dark web, point-to-point protocol or system for routing these messages. And this is going to become a DIDComm user agent reference application, because what we're going to do is take this user experience and we're going to bolt it onto a DIDComm network. And so in that DIDComm network, you'll be able to use DIDComm messaging for sending the text messages to a group of people using authenticated encryption, but you can also send verifiable credentials, for example, the business card in the lower left here. In yesterday's talk, we talked about verifiable credentials, and we talked about an example of the person schema from schema.org. And it's actually this Jane Doe professor at the Whiteworth Institute. And so when that is sent to all the parties in this group collaboration, chat reference application, that verifiable credential can be automatically rendered and shown here in the UI. In terms of DIDComm notation, a DIDComm user agent uses this graphical element. And here we see that DIDComm user agent, DIDComm notation being added to our architecture reference model. So this is the layer 5 DIDComm agent architecture reference model. It's the same as the layer 4 model, which is the mesh network model, but only with the addition of the user agent. The user agent will also work in layer 2 and layer 3, where you're just doing point-to-point messaging or point-to-point messaging with attachments as well. Here's the last model. We started numbering them from 0, so there's seven layers in the model, in the DIDComm architecture reference model. People ask me, where does Web 7.0 come from? Well, it actually came from the fact that there was 7 layers. There's two other explanations have been put forward. One is if you start with Web 1, Web 2, Web 3, Web 5, and Web 7, we're using prime numbers. So the next one after Web 7 will be Web 11. Or we're very close to having a Fibonacci series, so that could be another way of numbering the different versions of the web. So that's just a little comedic sidebar. The reason why Web 7.0 is called Web 7.0 is because there are 7 layers. Again, Web 7.0 was inspired by the Groove Workspace product, a decentralized group collaboration platform. It's actually a Windows application that ran on a Windows computer. You'd create workspaces. You could add tools for managing calendar, a tool for managing files, tasks. You, as a Groove business partner, Parallel Space was able to create custom Groove tools, such as a fully integrated version of Microsoft Outlook that ran both on the Microsoft 365 network, as well as spanned the Groove decentralized network, which was kind of cool. Many different kinds of custom applications were built for the Groove platform. So inspired by that, we have the layer 6 Web 7.0 architecture model. The red line, again, is the demarcation between the DIDComm network at the bottom for message routing and the Web 7.0 network at the top, which is where the agents live and where the virtual web drives live. Virtual web drive is an abstraction for TBD, decentralized web nodes, solid pods, and Trinity graphs. And if we think of the example of that group collaboration chat reference application, you see that at the very top in the center. It's a user agent. Whenever you click send, it's going to take that text that you type in. It's going to create a DIDComm message, send it to its agent. Its agent's going to take that and distribute it out to all the agents that are members of that group collaboration chat group. Similarly, if somebody using that application wants to send out a purchase order or a business card, they can attach that to a message and either send it to a particular individual or send it to everybody that's in the group. For Web 7.0, for layer 6 Web 7.0 to be complete, if you will, we also need to identify where the different kinds of DIDComm networks fit in. So the blue dots that I've been talking about, that's the DIDComm over HTTP network. But we could also have DIDComm over libp2p, you could have DIDComm over WebSockets, DIDComm over gRPC, DIDComm over Bluetooth as well. And so what we see above the red line, the way that agents do outbound processing and inbound processing, etc., the way the DID registry works, that can apply to any of these other networks as well. In addition, and it's not really highlighted here, but there could be gateway routers. So between the blue dot number 1, which is on the edge of the HTTP network, it could talk to a network gateway agent on the P2P network, on the WebSockets network, gRPC network, or Bluetooth, so that we could have full interoperability. That word that I try not to use, at the DIDComm network level as well. But certainly from agents and clients running above the red line, they can call into any of those networks fairly quickly. Okay, let's try and wrap up. So future directions. So we've got to this point, right? And as I looked at this picture and I realized what we're talking about, it's a world of agents, a world of trusted personal agents communicating with each other, and there are no websites. It begins to look like a network operating system. It begins to look like a message passing based network operating system. And kind of look at the history of operating systems. I've used most all of these. Um, I think this could evolve to being what I call the DIDComm operating system, or DID-DOS. And it would be interesting to imagine a DID-DOS world that powers Web 7.0. And in yesterday's talk, I talked about a Twitter conversation with Ray Ozzie where I said, as a stretch goal, perhaps Web 7.0 could lead to the Uberization of cloud computing. And I think what we've seen is a possibility, what we've seen is a glimpse of that happening, where the operational components of a cloud computing world become encapsulated as DIDComm agents, and we use DIDComm routing to connect them together. Those DIDComm agents could be deployed on local computers, unused resources on local computers, on servers, on little Raspberry Pis, in large roomfuls of Raspberry Pis, on huge cloud servers, that we could actually get to the point of what I call the Uberization of cloud services, and perhaps over time the deprecation of Microsoft Azure and the deprecation of AWS. It's just a thought, an interesting thought. In terms of looking at how Web 7.0 can evolve, I created this kind of roadmap meta model. And to make it a little more understandable, I put some points on the meta model. And so the idea is that the circle, the inner circle there is labeled Web 7.0. That represents all the things from a roadmap perspective that we'd want to realize to fully realize that initial version of Web 7.0. So if we look at the names around the periphery, there's different DIDComm libraries and language bindings. So there's Akapi and, for example, Okapi, and the language bindings, Python and C# respectively. There's different kinds of crypto libraries that could be used. The DID registry for 7.0 is going to be the universal DID server, and it's going to run, the DID over DNS protocol. There will be actually a DIDComm protocol, custom DIDComm protocol that will run on top of that, which will give you more of a DID resolution type experience using the 4 primitives. There's the core, DIDComm protocols that we've been talking about. The verifiable data registry is kind of out in the open there. It depends on what DID methods we support. DID-ION is a leading candidate, and so that would be the Bitcoin verifiable data network. DID methods, DID web, DID peer, DID key look like the most interesting ones right now. Maybe in 7.0, all we do is the HTTP transport, and maybe it's just the point-to-point topology and not the full mesh. Maybe the full mesh comes for 7.1. Because I'm a little bit biased towards the Microsoft tools, I put Visual Studio Code and Visual Studio itself on there. But this is an interesting way to envision or imagine and plan how we can get to Web 7.0, how 7.0 can become 7.1, 7.2, etc. To conclude, we've made it all the way from layer 0, REST over HTTP, to the Web 7.0. We can begin to imagine now this right-hand mission or vision of creating Web 7.0 that connects individuals to each other via their trusted personal agents. We can imagine a roadmap for that. Explain it to our friends and family. We have some pretty simple diagrams that we can use. We can understand and compare and contrast how this is different from Web 2 and Web 3, and that they both run on the internet. A lot of people need some clarification between, the web, what's the web and what's the internet. Kind of tied into the roadmap discussion is, technology adoption models. I have a blog called the Comprehensive Taxonomy of Technology Adoption Models or something like that on my blog. One of my favorites is called the Social Evolution Model. And if you look at the light blue boxes, it comes from a book whose title I remember, but the phrase out of that book that I remember, it's called The Peopling of the Earth. And it's how people moved from the populated parts of the earth to the underpopulated parts of the earth, millions of years ago. So there was always somebody called a wanderer, somebody who left their tribe to share their knowledge and wisdom with others. So I guess I'm the wanderer as far as Web 7.0 is concerned. That wanderer might team up with a small group, a party of explorers. That party of explorers might become a family unit or a clan. In turn, that family unit might in turn become a community or a band, and ultimately multiple communities or bands might become a society or a tribe, and so on. So it's the idea that it starts out somewhere, you attract some followers, those followers group themselves into family units, communities, and tribes. It's not really so different from the classic technology adoption lifecycle model, where you have a small group of innovators who then feed into a group of early adopters, and then there's the mainstream represented by the tallest part of the bell curve, the early majority and the late majority, and those mainstream users, they look across the chasm to the innovators and early adopters to see, is this stuff for real? Is this stuff going to work? What are they building with it? What are the case studies? What are the use cases? So as innovators and early adopters, we have a huge responsibility to feed the mainstream. The laggards we don't care about because they'll never adopt anything, so we just leave them there to fill out the right side of the bell curve. But whether you like the social evolution model, the way that this can be grown, or you like the technology adoption model, we have some explicit models we can use to grow zero. I think this is the last slide. So what do you do next? Where do you start? Well, start by building out the sample projects that are provided for each layer. I've got code for all of layer 0, layer 1, and layer 0 and layer 2, and part of layer 1. I'm doing some refinements on the DID registry, the Universal Data Server. But ultimately, there will be code for every layer in the DIDComm-ARM. Start using the notation. Start using it to design simple Web 7.0 networks or Web 7.0 projects. Just using direct point-to-point message routes. Number 3, there is a tool set out there that I've built called the DIDComm Superstack. You can go to YouTube and Google DIDComm Superstack, and you can start building these apps today. Number 4, will evolve your designs to include a DIDComm network. So start to think about how advanced message routing and disconnected agent support is going to work. Maybe you can become a key contributor to supply the DIDComm network router agent technology. And most of all, have fun. So that's it. I hope you've enjoyed this talk. I hope you have had a chance to look at the previous talk, I've tried to make this one make sense, somewhat standalone on its own. You can find me on Twitter. You can find me in the DIDComm Discord channel. I'm on LinkedIn. I'm pretty easy to find. And again, thank you for your time.